Welcome to lesson 2 of the binomial expansion in year 2. Today we're going to look at using the binomial expansion to find decimal approximations of irrational numbers. We're entering into the problem solving tier of what we aim to achieve in this chapter. We've seen one use of the binomial expansion. We can evaluate expansions up to as many terms as we like and multiply those expansions by other non-expansion expressions such as linear expressions. So we've done a lot of stuff already. So we're going to just have a look at some of the more interesting uses of the binomial expansion today in its new form. So what I've done, I've provided you with the definition again. So it's here. And you'll be referring to that quite regularly throughout the lesson. Okay, and please don't forget, of course, that this restriction on B is really, really important. And that restriction enables us to use any real number for n as well. All right, so without further ado, please pause the video and can you try the first 4 warm-up questions, please? Okay, let's have a look at question 1. So you've been asked to expand and simplify where possible. Now, if we have a look at the right-hand bracket, so we've got a quadratic expression there. A good thing to do would be just to let's start with a 1 here, and we'll multiply everything inside this bracket by 1 first, which is easy enough, isn't it? So let's do that. So this expression is going to equal, first of all, 1 subtract x plus 1/2 x squared. That's just simply multiplying everything by 1. And I alluded to this in the previous lesson. If you consider, well, this can be the constants column, this can be the x column, and this is the x squared column, then as long as I'm consistent with that, it'll be easy for us to add like terms. So for the next part, we're going to multiply all of this by the plus 2x. So let's do that. I'll do it in a different color. So that's plus 2x. So plus 2x multiplied by 1. So that's going to be plus 2x. Okay, we're putting that in the x column there. And then we have plus 2x multiplied by negative x. So that's going to be negative 2x squared. And then we have plus 2x multiplying the plus 1/2 x squared. All right, so the 2 and the half will cancel to give 1, so that's going to be plus x cubed. All right, now let's add our like terms vertically. So we've got to add our x terms there and our x squared terms there, and we have 1 and an x cubed remaining. So if we do that, we'll get 1 minus x plus 2x is plus x. Plus 1/2 subtract 2, it's going to be negative 3/2 x squared, and then plus the x cubed that's left over. So it's just a little strategy for doing that, okay? You can do it whatever way you like, but I think that works rather well. All right, so moving on to question 2. This is a very useful skill in this topic, and this crops up in the exam questions. We have to write 0.72 as a fraction. So it tells us to do this. And we have to show that if we take the square root of that, we get 3√2/5. So pay close attention to this and maybe refer back to this later. If I want to write 0.72 as a fraction, well, the easiest way to do it is to obviously, that will be 72 hundredths, which is essentially what 0.72 is. Now, what if I want to take the square root of that? Well, therefore, the square root of 0.72 must equal the square root of 72 over 100. So we're going to bring in our rules of surds here. Now, if I'm square rooting the whole fraction, it's the same as square rooting the numerator and the denominator separately. So this must be the square root of 72 divided by the square root of 100. Okay, using the rules of surds. Okay, now the square root of 72, I'd like to simplify that if I could. So let's think of factors of 72. If you're not confident with this, we want to find a square number that is a factor of 72. Okay, so we've got 1 and 72. Let's 2 multiplied by 36. Now 36 is a square number, okay, and it's the biggest square number that divides into 72, so that's good. So maybe I can split 72 into 2 times 36. So let's do that. So it's going to be, in fact, I'll write it as 36 times 2, so it makes more sense. So we're taking the square root of that. And the square root of 100 is, of course, 10. So I can replace the denominator with 10. Okay, and then I can use another rule of surds, the product rule of surds, if you like. So if I take the products of the square root of a product, it's the same as the product of the square roots. So that's root 36 multiplied by root 2 over 10. Okay, and it's quite easy now. So this is going to be 6 root 2 over 10. And obviously the 6 and 10 have common factors of 2. So this is going to be 3 root 2 over 5. Okay, great. So that's that one done. So question 3 is just an exercise in working with the range of validity. So it's where the expansions are valid. Now you've got to be careful here. There's you might be caught out with this. So let's have a look at the first one. We have 1 plus 5 over 4x to the power negative 12. Please, before you get carried away by writing down the range of validity, please check that this is going to give us an infinite expansion. Okay, we have a negative power. So that means our n equals negative 12. Now that puts this in the bracket where we have to, well, not in the bracket, but this means that we are dealing with an infinite expansion, which means that only certain values of x are valid. Okay, so therefore we can use this part of the definition. We're not interested in the expansion itself, we're just interested in the range of validity. So our b value, of course, the b value here is going to be this amount of x that you have here. Okay, so we can replace those. So let's do that. So minus 1, and then I put the b value in like that, and then we just make x the subject in the inequality. So if I multiply by 4 and divide by 5, okay, so there's our range of validity for that expansion. Now, the second expansion, you'll be forgiven for writing down exactly the same answer once you've done a bit of manipulation. Now, you don't need to do that, of course, because as I said earlier, if you're raising this to the power 120, your n is a natural number, isn't it? So n equals 120, which is a natural number. So this is valid for all x. Okay, so it doesn't have a range of validity in a sense. Its validity any real number, it will work absolutely fine. It's a linear expression. Okay, so I hope you weren't caught out by that. Maybe some of you were. For the last example, we're back to, we're resuming order here. So we have -1/2 here. So that means our n will provide an infinite expansion, which means we have to be careful which x values we substitute in. So we just have to write down what our b is. So the b, of course, is, so the b value is going to be -4/5. So we replace our b with -4/5. -4/5 x, I should have said. Okay, and this time we have to multiply by 5 and divide by 4 and divide by -1. Once you've done all that, you'll notice the negative doesn't actually affect the inequality at all, really. So you're absolutely fine just to write -5/4, multiplying by 5 divided by 4. Okay. Maybe you've done an extra step, but it's not necessary. We went through that in the previous lesson. Okay, so those are your range of validities in those questions. So a nice little question, that. So we've got two with infinite expansions, one without, which is valid for all real numbers. Okay, and then the other thing we have to consider, which comes up in exams as well, is when we have a product of two expansions, and you may be asked to do something like this. So please note, of course, that both of these products are going to give us a range of validity for x, which is bounded. Yet neither of these are going to be valid for all real numbers. So let's consider each one separately. So I'm going to call this one number 1. I'll call this one number 2, and let's have a look at 1 first. So the range of validity so we take our b value, so it's going to be x/5 in this instance is sandwiched between -1 and 1, not including both. So therefore, multiply everything by 5. That means that I can only input x values between -5 and 5. And I could demonstrate this on some sort of number line. So if I put a number line here like this, so 0, 1, 2, 3, 4, and 5, and then -1, -2, -3, -4, and -5. You know how to draw these from lower school. So from -5 up to 5, so we can't input 5 or -5, so we use a hollow circle, but everything in between is valid. So that would be for 1. Okay. For number 2, which I will do in green actually. For number 2, the range of validity, well, in this instance, it's going to be 2x/5 between -1 and 1. Therefore, I've got to multiply by 5 and divide by 2. So that's going to be -5/2 and 5/2. All right. Now, this is going to be different. So the range of validity for this is 5/2. So that's 2.5 and -2.5 respectively. So it's only valid between those two values, okay, that I've indicated there. So what does this mean? Well, as a product, for the first bracket isn't too much of a problem. I'm allowed to input anything from -5 up to 5. However, the second bracket is more restrictive. Okay, in the second bracket here, I'm only allowed to input from -5/2 to 5/2. Now, if that's the case, that forces me to consider only the values between -5/2 and 5/2. Okay, I have to pick the strictest restriction, if you like, the most limited restriction, because the x values have to be valid for both expansions. So this means that I just choose the strongest restriction between the two. So the range of validity overall has to be the strongest restriction you can get from both of these, which is that one. All right, and we've finished. Worked example 1, this is our first application of binomial expansion, and what we're going to do is we're going to use it to approximate root 2. That's in part B. You'll need your class whizzes for this one. Okay, so the first thing to do is find the expansion of 1 subtract 2x, all square rooted up to including the x cubed term. So please be aware of that. Okay, it's really important, the x cubed term. And let's write down what we're actually expanding. Well, 1 subtract 2x, of course, so it's 1 subtract 2x. Okay, and the square root, as you all know, means that we've got the power 1/2. So let's write down, so for part A, let's write down what our n and our b are. So I'll do that. I've just highlighted the n part, of course. So n equals 1/2, and b, I'll just highlight that. So b, remember, including the sign, would be all of this. It's the x part. All right, so that's my b. Let's write that down. So that's going to be -2x. Please don't forget the sign. It's incredibly important. All right, so now we can complete our expansion. So I'll just partition that off. So 1 subtract 2x is the power 1/2. And make sure you've got the definition in front of you for this. Is going to equal 1 plus n times b. That's 1/2 multiplied by -2x. Okay, so that's the first two terms done. Plus 1/2. So that's n multiplied by n subtract 1 over 2 factorial. And then we bring in the b squared. So that's -2x all squared. Okay. Right. And then we need the x cubed term. So it's n multiplied by n subtract 1 multiplied by n subtract 2 over 3 factorial. And then our b is cubed, so that's -2x cubed, and then plus some more terms. All right, so we've got 1, 1/2 of -2, so that's going to be -x. And remember, I'm not going to do too much in one go. Plus 1/2. Now, 1/2 subtract 1 is, of course, -1/2. 2 factorial is, of course, 2. And if I do -2x all squared, multiply that by 4x squared. Okay, Negative 2 squared is, of course, 4. X squared is, of course, x squared. All right, the next term, so I've got 1/2. A half subtract 1, same thing again. You should have replication there from the previous term. And then a half subtract 2. So 1/2 subtract 4 over 2, if you like. So that's going to be negative 3 over 2. Over 3 factorial, which is, of course, 6. And then negative 2 cubed is, of course, negative 8 x cubed, plus some more terms if necessary. More tidying up now. So we have 1 subtract x. Now, let's have a look at some cancellation here, perhaps. We have 4 and 2, which will cancel. So that's going to be 1. That's going to be 2. The 2 will cancel with the half, so we're going to be left with negative 1/2. Okay, because everything else is just going to simplify to 1. So that's good news. So we have negative 1/2 x squared. Notice the pattern. We have 1, and then we have negatives all the way along so far. I'm anticipating another negative now. Let's have a look if there's any cancellation in the x cubed term. Well, we do. So we've got 6 and negative 8, so there'll be some simplification there. So that's going to be negative. It's going to be negative 4 divided by 2 and 3. Okay, the 3's will cancel here as well. So let's just be very careful here. We have negative, a negative, and a negative. So it's definitely negative. There's 3 negatives. We have 4 over 8. 2 cubed is 8, so that looks like it's a half again. So it looks like we've got, that's our pattern. And again, if you're uncomfortable with that, please use your calculator. There's no reason why you don't have to. Okay, it's absolutely fine if you want to do that. All right. So let's move on to the next step. There's our expansion done. We've done everything they required in part A. It asks us, or it tells us, by substituting x equals 0.01, find an approximation for root 2, write down your full calculator display. Well, I just want to emphasize something here before we do that. Let me just block this off. Remember, of course, that what we have just discovered is an expansion which has a range of validity. And I know it doesn't ask for the range of validity, but it is important to be aware of it in this situation. All right, so the range of validity is where b is sandwiched between -1 and 1. So therefore, if I do that, my b value is, of course, -2x. Okay, and if I divide everything by -2, okay, and then obviously the inequalities will swap round. So I've skipped a step there, but we've done this a few times now. This is valid only between x equals -1/2 and 1/2. So I'm just gonna write down a sentence, or and I just want you to acknowledge this, because this is an important point. Okay, so what we have just discovered is that the square root of 1 subtract 2x is approximately equal to 1 subtract 1/2 x squared, subtract 1/2 x cubed, only when, I'm going to underline only when x is between -1/2 and 1/2. And we saw in the first lesson, didn't we? This is a nonsense statement if you're outside this range. All right. So this is all fine. This is absolutely fine. But as soon as you step outside of that range of validity, you know, intuitively, you know, you're going to get a nonsense statement. Okay. Right. So now we've acknowledged that. I'd like to move on to part B, and we can see clearly we're allowed to sub in 0.01 because, of course, 0.01 is in our range of validity, isn't it? So 0.01 is perfectly fine between a half and between minus half and a half. So we're allowed to sub that in, and we need to find a decimal approximation. Okay. Now, I'll just have to create a bit more room, and then we'll carry on with part B. So for part B, what I've done, I've just erased all those notes. You have a bit more space than I have, and I've just rewritten our expansion from part A with the restriction. So for part B, let's sub in x equals 0.01 into the left-hand side of that approximation. So consider the left-hand side, which is, of course, the square root of 1 subtract 2x. All right. So when x equals 0.01, square root of 1 subtract 2 multiplied by 0.01 is going to equal, now let's just have a look at this. So it's going to equal the square root of 1 subtract 0.02. Okay. All right, so I'm just subbing it in. I can simplify this. So this is going to equal the square root of 0.98. Okay, so at the moment you might be a little bit confused as why have we substituted in 0.01? Well, we're allowed to because it's inside the range of validity. Well, that was okay. So it's a value we are allowed to sub in. So I know it's going to converge on this number. But when I substitute it in, of course, I get 0.98. And my aim is to approximate root 2. Well, 0.98 looks nothing like root 2. So we need to think, how can we simplify this? We need to somehow create a root 2 from this surd here. Well, we can do this, and we saw a little demonstration in the starter, in the warm-up on how to do this. The first thing to do is to consider 0.98 as a fraction. So you might want to make a note of this. So we're going to write exactly the same as we did earlier on. So write 0.98 as a fraction. Now, once you've done that, it's a really important step. I'm going to asterisk it. Once you've remembered that, then the rest of it is just simplifying surds. So therefore, we're going to have the square root of 98 over 100. Okay? And that's going to equal, okay, so we can use one rule of surds, 98 square rooted over the square root of 100. Okay, so this is looking good, which equals the square root of 98 over 10. Now then, can we simplify the square root of 98? Well, you should remember from way back right at the start of the course and in your GCSE course, let's think of factors of 98. We want the biggest square number. So factors of 98, I'm just going to make a note here. So obviously 1 and 98. Does it divide by 2? Well, yes, it does. 2 lots of 49 make 98. Oh, isn't that wonderful? It's a square number. Okay, 49 is a square number. So we can replace 98 with 2 times 49. And remember, of course, we have the 2 on the left-hand side. We are trying to approximate root 2, of course. Yeah, so there's another clue there. It was going to be the 2 all along because we're trying to approximate root 2. Anyway, see how it all knits together nicely. So this is going to be the square root, or change to blue, never mind, of 49 multiplied by 2 all over 10, which equals, okay, the square root of 49 multiplied by the square root of 2 over 10, which equals 7 multiplied by the square root of 2 over 10. So we have simplified the left-hand side. Okay, I'm just going to partition the board here. Now, we've done a lot of work on the left-hand side now. We've substituted everything in. We've simplified to 7 root 2 over 10. Let's put it all together. So, therefore, when x equals 0.01, okay, the left-hand side is approximately equal to the right-hand side. Now, the left-hand side is, of course, 7 root 2 over 10. We've just done all that work, which is approximately equal to, now what we have to do is we have to substitute the x equals 0.01 into the whole thing. So we have to substitute it into the right-hand side. Okay, in other words, we have to substitute it into all this. Okay, which is easy. We can do that on your calculator. So if we substitute it into all that, we're going to get 1 subtract 0.01 minus 1/2 of 0.01 squared minus 1/2 of 0.01 cubed. Okay, so therefore 7 root 2 over 10 is approximately equal to, now I'll let you do this on your calculator. If you sub in those numbers, you should get this, fingers crossed, 0.9899495. So how do we get root 2? Well, root 2 is sat there waiting. It's waiting to be made the subject. Okay, so we need to multiply both sides by 10 and divide by 7, and we have our approximation. So therefore, the square root of 2 is roughly equal to 10 over 7 multiplied by what you got in the previous part, which was 0.9899495. So therefore, and it should look like root, I mean, if you don't get a number close to root 2, you've obviously done something wrong. Now, if I write down my full calculator display, I get 1.41421,357,1. So that's my approximation. Now, for example 2, we have a similar situation. We have to make a substitution into an expansion. And in addition to that, we have to find the percentage error. So what I will do is I would like you to try part A as an exercise. We've done several of these expansions. So just pause the video, please. Have a go. You don't have to do it on your notes. Maybe you can do it in rough or on a whiteboard or something. And then check with me in a few minutes once you've done that, and just pause the video and then we'll carry on. All right, so let's have a look at part A. And same as usual, really. We just have to write down what the power is. So obviously the square root means 1 plus 3x to the power 1/2. This also means, of course, that n equals 1/2, and your b value is equal to 3x. So we simply substitute those into our expansion. So this is going to equal 1 plus nb, so that's 1/2, multiplied by b, so that's 3x. And then the third term gets a little bit more complicated. So 1/2 multiplied by 1/2 subtract 1 all over 2 factorial. And then we bring our b in. So that's 3x and all squared. And then, as is customary, we need up to the x cubed term. So again, please read that carefully. Don't do more work than you have to, and don't fall short. So plus 1/2 multiplied by 1/2 subtract 1, that's our n, of course, multiplied by n subtract 2. And it's very rare that you would ask to do anything beyond the x cubed term, as you've seen already, because the numbers get very big and complex. And then we've got b, which is 3x all cubed, plus some other stuff. So hopefully you've got your answer in front of you. So this is going to be 1 plus 3 over 2x. If you've got that right, give yourself a pat on the back. That's good. Then we just evaluate this a little bit. Again, I don't like to do too much in one go. I like to take my time with this. 1/2 subtract 1, so that's going to be -1/2 over 2 factorial, which is 2, multiplied by 3x all squared, which is 9x squared. And then for the third term, so again, we've got 1/2, -1/2, and then -3 over 2, all over 6, which is 3 factorial, and then we've got to cube 3, so that's going to be 27x cubed. So you might have all this loaded into your calculator. So this is going to equal 1, add 3 over 2x. Okay, now the 9 and the 2 aren't going to cancel. We have a negative here as well, so -1/4 divided by 2. So I suspect we're going to get -9 over 8x squared. And in the final term, well, we do have some cancellation. We have the 6 and the 27. I can simplify that definitely. What have we got left over? Well, if I divide by 3, obviously we've got 2 there and 9 here. And I can't simplify any more than that. So I have 3 times 9 is 27. Let's just fill that in. So it's 27. We have a double negative, so that's going to be plus, and that's in keeping with the pattern of plus, minus, plus, minus, plus, minus, etc. Okay, so it's going to be plus 27 on the top, and then we have 2 cubed in the denominator of the fractions, and then another, divide that by 2, so it's 2 to the power 4 essentially, which is of course 16x cubed. Okay, so hopefully you got that. That seems to be the expansion up to and including the x cubed term. And it does say to simplify each term. If you notice, these are all fractions, aren't they? So please simplify your fractions like I've done with the cancellation. Right, moving on to part B. Part B, we have to show that when x equals 1 over 100, the exact value of f of x. Oh, that's a typo, isn't it? That should be g of x. I apologize. Please change that. Very unprofessional. The square root of 103 over 10. Well, let's just sub it in and find out what happens. So if I substitute that in, that's going to be 1 plus 3 lots of 1 over 100 inside the square root. Okay, now this 3 over 100 is of course 0.03. So that's going to be 1 plus 0.03. It's better to go back to decimals first, isn't it? Which equals the square root of 1.03. So how do we get the 103 inside the square root? Well, once again, this is the key step, and I made a big fuss of it last time. What we need to do is we need to write 1.03 as a fraction. Okay, and if you do that, everything will fall into place. So therefore, we have the square root of 103 over 100. And the answer just pops out, doesn't it? So that's going to equal the square root of 103 over the square root of 100, which equals the square root of 103 over 10, which is to show that, so we have shown that. Now, part C, we have to find the percentage error used in making this series expansion. Remember, these are approximations, okay? If we did an infinite expansion, we would get the exact answer, but obviously that's not possible. So we want to see how good are our approximations. Well, let's have a look. We've got the left-hand side of our expansion here, which I'll just indicate, which is the 1 plus 3x. We've substituted in 0.01. We've done that already, and we did that here, and then we got this result here once we've done a bit of manipulation with the surds. So now we need to make the substitution into the left-hand side. Now, I beg your pardon, the right-hand side. So when we do that, for the right-hand side, and we compare the results, we should be able to see how good our approximation is. So for the right-hand side, we'll have 1 plus 3 over 2 multiplied by 0.01, subtract 9 over 8 multiplied by 0.01 all squared, and then we're going to add 27 over 16, and then it's 0.01 to the power 3. Okay, and what we know is that this is going to be approximately the square root of 103 divided by 10. Okay, and I've just realized I've swapped the sides around, but that's generally the gist. So we substitute x equals 0.01 into both sides, i.e. into here and into here, and then we've got our approximation. Now, if we evaluate this, what do we get? Well, if you whack all that into your calculator, as I've already done, you will discover that the square root of 103 over 10 is approximately equal to, and just check your results with me, 1.014 889 188. So that's what you get when you evaluate all of this. Okay, so you should get this number here. Now, what does that tell us? Now, that is an approximation. So to get the square root of 103, of course, we've got to multiply all this by 10. So let's do that. So therefore, the square root of 103 is going to be approximately 10 times that. So that's going to be 10.14. So just times it by 10 on your calculator. 889,188. Okay, so I think that must have been a terminating decimal. Okay, so that's our approximation. So how good is it? Is it close to the real thing? Well, we need to work out the real thing. Your calculator will do that. You'll just have to press the SD button once you've typed in the square root of 103. So on the calculator, the square root of 103 is equal to 10.14889157. Now, immediately you can see this is an excellent approximation. But how close is it? I mean, what is the percentage error? Well, the percentage error, which I'll do over here, the first thing we need to work out is the difference between the two values. Now, you can probably see, if we just look at the values we've been given here, in the approximation, it ends in 188. All the other digits are the same. It's ending in 188, just right here. And in the actual value, which obviously is an irrational number, but on the calculator display ends in 157. So the approximation is greater than the exact answer. So it's an overestimate. So let's just work out the difference. So the difference so we just subtract the smaller one from the larger one. So we're going to get 10.14889188 subtract an almost identical number, 14889,157. Okay, now when you do that, you get a very small number indeed. Now, depending on which value you use, will depend on your result here. So if you use the exact value of the square root of 103, what you will get here is 3.149. I'll leave it like that, multiplied by 10 to the power -7, which is an incredibly small number. If you use the values I've written on the board here, you'll get 3.1 times 10 to the -7. So either way, we can just leave it as 3.1 times 10 to the -7. Okay, we're not asked for a particular degree of accuracy here. Usually it's the three significant figures, but it doesn't really matter. So for the percentage error, that's the difference. We need to take that difference and divide it by the actual answer, and then calculate that as a percentage. So let me just stop using this red. Okay, so percentage error is going to equal the difference. Difference is always a positive number, remember, over the actual, and then you multiply that by 100%. So in other words, it's going to be the 149 times 10 to the -7 divided by the actual answer, which is the square root of 103, and then multiply that by 100%. Now, if you do that, I'm just running a little bit out of space. you should get the following. So 3.055 multiplied by 10 to the power -6. And that's a percentage. So what we have just discovered is that in this instance, this binomial expansion is incredibly accurate. Okay, there's very little difference between using the expansion and the real deal. Now then, that concludes the worked examples. Again, there's an exercise for you to try where you can put some of these skills into practice.